Good evening to all of you. Now I'll be presenting my data mining project entitled Are There Dormant Neurons Outside Reinforcement Learning? As a quick overview of the project, first I wanted to point out that in reinforcement learning was shown that some neurons stop changing as the training progressed. These are the neurons called dormant neurons. The activation for these neurons are very small. So therefore the dormant neurons phenomenon characterizes a training process whose number of dormant neurons increases over time. One key factor in this phenomenon is the non-stationarity of the targets. And this led us to wonder if this phenomenon was specific for the reinforcement learning of or if there was actually another context in which we could see this phenomenon. Specifically, we explored if such phenomenon occurred in an online training learning context. For that, we proposed and designed an experimental framework in which we trained a deep neural network in a forecast prediction task, and we monitored and examined the activity of the neurons during the learning process. A little background for this project. As primary motivation for this research, we have the research that showed that within the deep reinforcement learning context we had the dormant neuron phenomenon. This phenomenon highly diminishes the network expressivity. So the authors proposed a method called recycle dormant neurons, redo, for in order to mitigate the dormant neurons impact, and they actually showed that this resulted in an improved performance of the model. And as second motivation for the research, we have that actually inspecting the network weights, it's very good when we want to gain insights into how the model is behaving, or how the model is learning, and how it would behave in the future. The methodology for this research is integrated by three main phases. The first one is the data pre-processing. We consider two data sets, and we used a data loader to load these two data sets, and in order to online train the model using these data sets. As a second step in the methodology, as I said before, we online trained a deep neural network, and as the training was going on, we evaluated the model using a progressive minimum square error, and we also recorded the neuron activations. Once we had the model trained, we conducted an analysis of the recorded neuron activations in the third phase, the dormant neurons analysis. We look for dormant neurons at each time for each layer as as we online trained the model, and after that we counted the number of dormant neurons for each time step to check if actually this number increased or not. The data used for this experimentation has two data sets. The two of them were collected by electricity transformers. The size of both of them is 70,080 examples. The features are the date, the high useful and useless load, the middle useful and useless load, the low useful and useless load. The period of time for both datasets is from 2016 to 2018. The difference between these two datasets is that one of them was collected in the region A of China, and the other one was collected in a different region, also in China. I included the GitHub link for these two datasets in case some of you wanted to take a look at it. Here we can see the behavior of the oil temperature, which is the target for these datasets, for region A and region B. This plot shows that actually it has a behavior of oscillations for both datasets. Using this data, we online trained the following model. We can see in the figure the architecture. It has 4 layers. 2 of them are dense layers, and the other 2 are long short-term memory layers. The input of this model is a window of 4 examples and a current example. So for each example, we have a history of 4 previous examples. The dense layers receive the window, and for each of these examples considers the 7 features. We'll left out the date, and the output of this dense layer that has a size of 100 was fed into the LSTMs, and we consider only the last time step output vector for the LSTMs, and after that we concatenated this vector with the current features vector, and this new vector was the input for the last dense layer, which received, as we can see, a vector of size 56, 50 for the last time step output vector of the LSTM, and 6 for the current feature vector of the current example. A little more details on the training process. We use loss function. We use the minimum square error. As optimizer, we use Atom, and we normalized the data because we saw that if we didn't do that, the performance of the model actually was worse over the training. So we kept a minimum and maximum for each time step, and we normalized the current batches with this minimum and maximum. And we also evaluate the method using the minimum square error for the batch in that time step. For each time step, we train for 5 epochs. Here we can see a plot of the target and predictions during the time, the training phase, as time points increase. They are actually, this is for both datasets, region A to the left and region B to the right. We can see that actually it's a very good estimate of the target. However, this goes up until 2,100 something batches. So we won't see here, but the last batches actually have an increase of the minimum square error. In this plots we can see what I was just saying. In blue we have the minimum square error scores across batches, and in red we have the minimum square error per batch. So for both datasets, the minimum square error increases as we go to the end of the time points, as we progress in the training. So the next thing, once we have the model trained, is to inspect the neuron's activity. We want to analyze if we have dormant neurons or not. For that, as I said earlier, we have while we were training, we recorded the mean activation of each neuron for each time step for each layer. So we have a total of 150 neurons. We consider this amount of neurons, and after training, we calculated a score that allowed us to actually determine if a neuron was dormant or not. For that, we compared to a threshold, and if actually this score was less than that threshold, the neuron was considered dormant. The score is specific to a neuron in a specific layer, and we use the mean activation of that neuron in that layer across all examples of that batch. We also normalize that number using the average. After we had the comparisons of the score with the threshold, this means that we already have the neurons that are dormant. We counted the number of these neurons across all time steps. Here we can see that for both datasets, we have the plot of the number of dormant neurons as the time increases, as the training progresses. So both plots, the plots above are the same as the plots below. We only considered a window of 10 time points, and we take the average of them, so we can see a softer line. But we can see that the trend is to actually increase the number of dormant neurons. So as results, we can see that the performance of the model using the progressive minimum square error metric deteriorates over time. The number of dormant neurons fluctuates between 0 and 50 for region A and between 0 and 75 for region B. And after inspecting the scores, we consider a threshold of 0.2. This allowed us to determine if actually the neurons were dormant or not. And after that, we could see that for the for each time step, the number of dormant neurons tend to increase as the training progresses for both datasets. So we can conclude that the dormant neuron phenomenon can negatively impact our model's performance. The experiments conducted suggest that actually this phenomenon can occur while online training, and in this particular instance, as the training progresses, the performance of the model worsens. So this can be due, or is likely due, to an increasing number of dormant neurons or neurons that are not contributing enough to the output. So as future work, we propose to apply mitigation techniques for the dormant neuron phenomenon as the one proposed in the dormant neuron phenomenon in deep reinforcement learning paper. We also recommend to experiment with datasets of a different nature or with different targets instead of being a function of time, targets that change with time. And we also recommend to explore other forms of learning, for example, generative adversarial networks, in order to explore non-stationary targets. The main references for this project is the dormant neuron phenomenon in deep reinforcement learning and the weight scale interpreting weight change in neural networks. So thank you so much for your attention. I hope you all gained some insights into the dormant neuron phenomenon. If you have any questions or suggestions, please don't hesitate to write to me. I have the email Anna_Arguelles1@baylor.edu. Thank you.